Hello, everyone, and welcome to another session of the Digital WE Days. My name is Silas and I will moderate this webinar today. Our topic of today is Inrush current of the connector. Our speaker today is Vamsi Krishna Gajula. He works as a field application engineer at Wood Electronic ISOs. Vamsi, welcome. Cool to have you here today. Current creates heat and connectors must handle it reliable. But can we exceed rated current for short bursts without risking failure? Let's find out. Stage is yours, Krishna.
Hi everyone, this is Vamsi Krishna. I'm working in Worth Electronics as a senior FAE. I've been in this company 15 years. Today topic for the digital day is inrush current for the connectors. So the agenda of this presentation is like inrush current. I'm not talking about what is the inrush current. I'm just discussing about what the selected component for the application is suitable for the inrush current or not. And discuss about the standards which we follow for the inrush current calculations, and then the most important thing, which is like inrush current versus derating current. What is the difference between these two, and how you can use this Joule curve to select the right component for the application which we are working. So when we talk about the inrush current, the question that comes into the mind is what is a good question? For example, if you are working for any application where your required current rating is around 6 amps, then working current is 6 amps, then you select the terminal block which is in a small size, which is 2.54 which has current rating 6 amps, which is very small on the PCBs also, which will fulfill, and which is a very cost effective product. But suddenly you realize that you are working for the application high current, like just like the motor applications where it required very high current initially, like maybe 1, 2 or 3, maybe 6 times of the current of the working current. So then what you will do it, then what we are going to be do. So then what, as a design engineer, we select the high current. So if it is a 6 times of the current, like if you calculate the current rating of 6 amps, then if you multiply with the 6 times, which is comes to 36 amps, and the selected component which we have 57 amps. As a design engineers, we always look for the margin, the safety margin. So if you look for the 57 amps, the size of the characters is also very high, and you have to spend more amount of money on the purchasing the component, and if you take the more space on the PCB. So as a design engineer, the question comes, is this the right solution, as the right way of selecting the component? But if you ask me, yes, most of the people will say that this is the right component. But today I'm going to talk about the some solutions which helps us to select the right component for the inrush current applications. So when we talk about the motor applications, for example, application issue like the application which we consider like two-wheeler e-bike, or maybe e-scooter, or maybe transformer applications or wireless applications, the tungsten lamp, now it is replaced by with LED bulbs and the capacitors. So all the applications which you are talking about will have inrush current challenges in the market. So how we are going to do face these challenges? So for that, we have done the some market survey, and we have asked the questions to the R&D. So the major question comes from the any application point of view is how to select the component, and how much time we need to put the induced current in particular connector, and what could be the size of the connector. So this is the questions which normally we have. So I'm going to answer these questions with some examples, 1 or 2 examples as per the IEC standards, which is mentioned like IEC 61058-1 and 1. So why I've selected this one is this is as you see here is switches for the applications, the requirement for the mechanical switches. So normally we use the mechanical switches to switch on the motor for applications. So that's the reason I've selected for this particular standards. So when we talk about the standards, first is what we talk about the resistivity load. So when we talk about the resistivity load, as per this standard, we can go 6 times of the rated current as is shown in the PPTs. So when we talk about the inductive load, so when you talk about load for the electrical load, so as per the again IEC standards, we can calculate 6 times of the rated current what we have mentioned in the data sheet of the particular component. The same way, when we talk about what you call the tungsten lamp bulb, which is now all replaced by LEDs. But if you see that tungsten lamp, it is multiplied by the 16 times of the rated current, which is very, very high for the 50 milliseconds. And if you talk about the 10 milliseconds, it has to multiply by the 10 times. So this is about the tungsten bulb. And the most important thing, the capacitor discharge. So capacitor discharge is not mentioned in the IEC standard, but whenever capacitor used to discharge the charging, the induce current issues or the challenges may come into the picture. So we need to consider even the capacitor discharging also when we calculating the induce current applications. Okay, by considering all these standards which we have discussed earlier and the market survey, we have defined the current working ratio. So what exactly this graph talks about? If you take about this is an x-axis talks about the time, which is in milliseconds, and the induced current peak ratio with working current. So what that exactly means? So if you want to use this selected component for what you say 2 times of the rated current, so how much time we have to calculate, how much time we can keep in the particular component. For example, if you take here, if you talk about the 2 times of the rated current, so let's say the working current, rated current which we are defined for the particular components is a 6 amps. Then if you multiply it by 6 with a 2, which is comes around 12 amps, then for the 12 amps we can use that particular component, but the time will be the 6 seconds only. Beyond that we cannot keep it the paint damage. If we talk about the 4 times of the rated current, which is again I can say 24 amps, yes, you can use still the same component, but the time duration of particular component will be reduced. So the question comes, well, will this work? Yes, it will going to work, but we'll also discuss how it is going to work. But before that, we also talk about some basics, which is it's not about the pure basics. I'll just take the few slides for that before that. So we all agree that every connector act as a resistor, and that every resistor will have a temperature. So whatever the temperature is there in ambient, the same temperature will be there in the resistor. So when we apply any current to them, so the resistor will start up heating up. So that we write up as the delta T, which is normally we call as the Joule's effect. So when we have this T and the delta T, what could be the total heat on the resistors? How do we get it? So the total heat on the connector will be the ambient temperature plus delta T, what we have. So if you see here, for the ambient temperature, we have mentioned in the Celsius. So why we have used the two different units? It is like the to make a distinguish between the ambient temperature as well as the delta raised temperature. Further, to consider this current rating and the temperature raise, we know all this formula like P is equal to R into I square, and delta T is given by K R and I square. So where P stands for the power dissipated by the resistor, R is the resistance, and I is the current, and delta K, I mean what not delta, no, it's a K which is also given in the Kelvin, and the K is defined by the constant, but is the value will keep on changing depending upon the resistance of the material and the environment. So what we can say is, if the temperature is proportional to the square root of the current, so that means if you double the temperature on the product, the current will be the 4 times of the particular temperature range. So how it is going to be happens is like if we talk about theoretical calculations, delta T is equal to K into R into I square, which is seen in the previous slide also. The measurement, if you talk about the current, can take the connector, and if you talk about the current which we double, let's say I is equal to 15 amps, and the gear which gives the delta T of the 15K. So if you double the current, like if you take about the current as 30 amps, but the temperature will be the 60K, which is 15 into 4 is the 16K. But it's not like if you double the 30, the temperature raise delta will not be the 30, it will be always 4 times of the current rating. So what exactly means, if you double the current, the delta T will be always 4 times of the temperature raise. So this is about all this basics. And how do it possible? So we can consider this application. So as per the UL standard. So when we talk about the any standard delta raise, if we talk about the UL standard, the delta T always below the 30K. For example, if we talk about this examples, the where the ambient temperature is the 50 degrees, but the total temperature in the connector will be the max 80 degrees temperature. So again, when we apply any connector, the temperature raise in the connectors will not happen very fast. So if we talk about the time versus temperature as shown in the graph, if you take a consider here, so the raise in the temperature in the connector, it will be gradually it will make to this one and reaches to the peak. And if you see that, it will always below the 30K, which is as per the UL standard. So if you zoom, consider the graph and make it the zoom very clear. And if you see here, what exactly happening here is like, if you zoom it the right side connector graph, and if you zoom it here actually, if you see it's exactly the current is like, if you talk about the 10 seconds, right, it took almost 10 seconds of time to reach the 5 Kelvin of the temperature, 5 Kelvin of the temperature. So if you keep on increasing here to reach the maximum of 30 Kelvin, it took almost 20 when 60 temperatures. But as a standard, we still respect the what you call UL standards timing actually. So how it is going to be happen? So for that, we do the one test here. We take about the terminal block which can support the 20 AWG wire, and we took the wire length of the 50 centimeters, and we applied the working current, which is a 6 amps current rating, and we have seen how this terminal block is going to be react. So when we applied this, so we have got this graph. So if you see this graph exactly here, again we have x-axis is the time and the temperature is there. So for working current, which is the 5 amps, it is well below, if you see that's blue curve, which is well below the 20 degrees of temperature. Which is like, that means that we are respecting the UL standard, which is less than of 30K. And if you consider the 8 amps current, which is, I cannot say 1.5 times of the working current, then if you see this one, it has been increased, it is grown above the standards of UL standard, which is after 180 seconds, the raised temperature is around 35 degrees of temperature. And if you talk about the 11 amps current rating, which is 2 times of the working current, so you can see the temperature is almost around 50, 62 or 63, which is, I don't know exactly, but maybe we can consider as a 63 Kelvin. So if we talk about this one, so the working current is 5 amps. So now we consider it as the 11 amps, which is the almost 2 times of the working current. And if you see the temperature range, it is almost 4 times of the working this one. This is like 15 amps we have. It is gone to 64. So like how we discussed in the previous slide, if you double the double the current rating, the temperature will be the 4 times of the current working current. And if you consider the other current like 24 amps, the raise of this 24 amps, that duration is very less. We can consider, still we can apply 24 amps in the connector, but the duration time is very less. And if you talk about 35 amps, it's very short time period we have to consider this. And then if you make it the pre-test induced current duration of 30K, what exactly is it if I take it about the 11 amps current rating? So if take about the 11 amps, how much time I can keep that 11 amps current rating in the connector is for 30K. We will take it as a 30K because the UL standard defines as a delta T is the 30K only. So if we take 30K, which is base 1, we can keep it for 35 seconds. So for 11 amps current rating for the same connector, which has a 5 amps working current, we can use for 35 seconds time only. So beyond that, it will go to the what you call 30K. Beyond that, it will go beyond UL standards, which we cannot consider these things. So to make it, I mean, we calculate now what we are is terminal blocks for 2-pole we have taken, and this is the current working ratio which we have defined this graph as per the standards in the market and this one, and then just compare it how it works. So if we take about the 11 amps, so as I told you that ratio, current ratio, which is 11 divided by 5, which is the 2.2 times of the working current. So if you plot the graph in the working current ratio, it comes exactly around 35 seconds, which we have seen yesterday in the previous slide. So now, if we talk about other current, which is again the 17 amps, which is the almost, I can say, more than three times of this current of working current, we can keep it around 15 seconds of time. We can consider to keep in the connector. And if we talk about the 24, which is almost five times of the working connector, so still that we can give it around 5 seconds, or maybe 5 or 6 seconds exactly. We don't. Then if we talk about 35 amps current rating, this thing, this will comes around this one. So now, even if you compare the results, test results with respective of typical current ratio with 30K and the current ratio of these things, how we can going to be plot the graph. So we have done what this, if we consider, this is the tested current ratio which we have done in previous slide, and this is the interest current working rate as per the standard switch. So if you compare this, what we are going to get exactly. So if you compare, this one is what we call is as the I measure was I needed. You can see this is the curve what we have tested, and this is the curve what we have as per the standard. So when we have seen that we have well within the range of margin, and we have very good three times of the margin what is required. So this is what we are going to get for the Worth Electronics. And then what we have done is, apart from that, we have done taking the 10 different points for the testings, and we have measured how much time we can keep that particular current, induced current in the particular connector. So then we have done the same kind of 10 different points test with the different connectors. If we talk about that, it is the product line what we have with Worth Electronics, and we have done this one. So if you take it, the maximum pole which we have taken is the 24 poles, and current rating, you can see again we took the 10 different times. If we talk about the MPC4, which has the 24 poles and the working current is 6 amps, so if we talk about the 6 amps, we can keep 10 minutes time. And if we consider about 3.6 time of the working current, you can keep it for 2 seconds, which is a 21.6 amps current rating. You can use the same connectors, but the duration of time will be the 2 seconds. And if we talk about the 16th time of working current, which is almost 16 into 96 amps, we can keep it for only for 0.1 seconds. And the same thing if we talk about the terminal blocks, which is has a 12 poles, which is a 5.08 pitch, whose working current is 12 amps. If you take it the working current as a 12 amps, you can keep it again 10 minutes. And for example, if you talk about the 16th time of these things, which is around 192 amps, you can still consider again it is only the 0.1 seconds times. So this is tested, but the question comes again, will really it works or not? So yes, it works. For that we have done one small test here. So what exactly is like induced current measurement was the delta was as for the time. So for that we need the thermal camera and the connectors which has the 12 poles and the cable also. So what interesting here is like this is the graph. So we have 10 different points. I can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points, and this is the rated current which we have this one. So if you initially this is a curve, the rated current is went for the maximum. So if you keep on increasing the rated current for the connectors, it will go beyond this one, but again it will be still below the delta T, which is less than 30K as per the UL standard. And rest, if you see this one, this graph, which is the rated not rated, is the induced current, and all these curves are well below the rated current of this current. So why it is happening like this? If you take about the this 2000 seconds, which is 16th pulse, the duration of two pulses, two what you call waveform of the two induced current shots, there is a gap of 5 minutes. So if you take the one, this one, it has reached almost 6 Kelvin delta T, and it is calmed down, and again it is 1 to 6 Kelvin. So why it is calmed down? Because we have given the 5 minutes time with between the two what you call the induced current shots. So this gives the system to cool down. Again, when we give the induced current shot, it will comes this maximum time and come in this cool down. If we do not give this time duration, what exactly happens is keep on adding this one, and it reaches to the beyond the UL standard, and at the end that may spoil the product actually. So further to this, now we talk about the MPC connectors, which we talk about. This is a induction current ratio with the time, this one, and this is which the same correct graph which we have zoomed in and see that how well if we apply the 16th the time of the rated current. So if we talk about the 16th current of this one, if we zoom this current this graph, we can see 0.1 times. And if we talk about the six times of the rated current, you can use this one, you can about 0.5 seconds on this one. So this is all about the induction current with the current working ratio. So now we'll talk about a derating current connectors for the induction current. So before that, I just gave a brief about the what is the derating current actually. So this is the derating current as per the UL standard. So if you take about any connector, that is the example I took it from the Worth Electronics product line, which is a 3.96 the pitch, the white to board connectors, and the current rating which we are given the 7 amps, and the operating temperatures which we are given is minus 42 105. And this is the UL rating curve driven by the UL standards. And if you see here, we have a x-axis, we have operating temperature, and y-axis we have applicable count. So when we talk about the operating temperature, so we have given the 85 degrees red color and 105 and 120, 125, 130. So when we take about this operating temperature, we need to consider 105 graph. And if you see like this, you can see that based on this graph we can calculate. So if we talk about the 70% the graph, when you say how much current it can, this particular connectors can carry at the 90 degrees of temperature is 4.9 amps. So this is how you need to calculate the derating curve. So detailed explanation is given by my another colleague in the another detailed digital video. So coming back to again the derating current, the curve without induction current. So when you're talking about the derating current without induction currents, so here we talk about the 80, we take operating temperature as 85 degrees. So when we calculate like this, what exactly happens is we take 85 amps and we take about 30k. So why we consider 30k is we know that 30k is the delta T which we are given the UL standard. So you subtract from operating temperature 85 minus 30k, so you get the 55 degrees. So once you reach the 55 degrees of graph here, you start decreasing the temperature in order to reach the 85 degrees of the operating temperature of the connector. So this is basic principle. As I told, the delta T is always considered the current. And one important thing which you need to consider is the connector internal temperature is always should be always less than the operating temperature. So if it exceeds the below above in the operating temperature, again the connectors will get into the product will get spoiled. So now, if you want to use it, the current rating with the security margins, a stable current will be the less than. If you want to use the rating curve with the induction current, then that 30k has to be split into the two times. So one is the stable current, which is less than 15 amps, and the 15k, and then the induction current always considered as the less than 50k only. So now we talk about the derating curve with the induction current. So when we talk about the derating curve with 30k, so we again consider the same like 85 degrees with the minus 30k and 55 degrees. We have to start reducing the temperature to in order to reach the 85 degrees of operating temperature of the that particular product. So if you talk about the inrush current, so what we have to do consider is the we have to as I told you that we need to split the 30k into the two parts. One is a stable current, another is the 15k is the subtraction what we have operating temperature. So we have to consider this formula, that is like I max is equal to square root of 15k divided by 30k, I max of 30k. So as per this formula, you have to limit the stable current of 70%. Suppose if you talk about we have 100% here, we talk about stable current, we have to subtract to the 70% only. So 70% we have to talk, and then we need to consider the 55 degrees, because again we have to subtract with 75 degrees. So here we are considered as 85 minus 30, 55 degrees. We have to consider 70% of the current, and 85 degrees minus 50k. So we get the 70 degrees of temperature. So this is the point you are able to use the still induction current until you can go for the 85 degrees of temperature. So this is thing, and final curve. So when we talk about this is the current left hand side, what we see is the UL derating with curves with plus induction current and this is the Inrush current working ratio, peak ratio applicable, this one for terminal blocks. So what we suggest is you can use this current, and whatever the we have done the testing, it is in a still air. If you want use it particularly like the data sheet is guard driver. So if you want to use your system, please always consider the ambient temperature. Check the temperature of the your systems. So if you want to do any testings, you can contact your local FAEs who can help you on the calculation of the product if you are not using the Worth Electronics product. Well, so whatever the rated current product, related product which we have defined and the tested is all the terminal blocks and the wire to board connectors what we have. Again, and whatever we have done, it is all the still air. Whatever the values or the graphs which we have shown is always in the still air gas air only. If we are using the product other than the Worth Electronics, as I told you that you can contact your local FAE, we can test it and we can give the absolute the values what it is required. Okay, I conclude my presentation here. Before closing my presentation, I would like to tell one thing that whatever I have discussed with regards to the Inrush current, so we have application note already there. So this is the link for the application note. So if we just click it here, it will take directly to the application note what we have written in the already available in the Wood website. So if you go through this application note, so whatever I've discussed, temperature, Joule, current, temperature ratio, and how do you calculate with regards to the Inrush current, rated current with the Inrush current calculations, and the examples which I've discussed in my presentations, and the timing. All this graph is being clearly explained in the application note. You can also, it is a free downloadable application note, and I think you have already seen the link. So now I'm done my presentation. If you have any questions, I'm open for a discussion.
Yeah, thank you, Vamsi, for your interesting presentation. Now we'll come to your questions. Before we start with the live Q&A, I will share the handout from the presentation from Vamsi. Now everyone can download it. Now we will come to your questions. So Vamsi, can you hear me?
Yes.
Perfect. Are you ready for the questions?
Yes.
Okay, very good. Then, first question. By increasing pitch of connector, can we increase the creepage, and clearance distance?
Yes, you can increase the creepage clearance distance by increasing the pitch, but I suggest the creepage and the clearance calculations depends upon the many parameters like pollution degree, inrush currents, and impulse current, and the standards which you are working. So you should consider all those points also.
Okay, thank you. Then, next question. Comes from Carlos. When it was spoken of the UL derating curves, what specific UL standard did it refer to?
When it comes to the derating curves, UL does not have any specific standard. It's like just like a UL standard only. We do not have any certification number like how we used to have for the connector or any passive components. Just we call it as a UL standard only.
Thank you. Then next question. It is a little bit longer. When we use a multipole connector for supplying high rated current and transist current required loads like PCI edge cards for IA clusters, does it make sense to consider the maximum current pole count for evaluating the current flow per pole? Or should we use additional E-counters like load balancers, etc., for reliable operation of the connector without any damage? So when it's too long, Vamsi, you can answer it by mail, but yeah, you can try
Maybe I prefer to give answer by email.
Yeah, okay. So yeah, Ishab, Vamsi will answer your question via email in the next days. Okay, then next question. How and where can we get creepage and clearance distance of connector?
Okay, this information you will not get, but you need to calculate, because when you talk about the clearance, it is the distance between in the air with adjacent pins, and the creepage is like this is the distance between adjacent pins to the plastic, just to the insulator material. That's where you need to calculate and get the information. But as a manufacturers, we will not be mentioning this information in the data sheet.
Thank you. Then next question comes from Oliver. Is there a degradation over cycles for having the inrush, or is that unaffected if kept under delta T of 30 key?
If you keep delta T at 30K, the current, the connector will not get any degradation. So we should respect the standards. So as long as we are respecting, there will not be any degradation of going to be happen to the connector.
Thank you. Then next question. Will be creepage and clearance distance the same for all connector?
No, this is not the same.
Okay. Thank you. Then I think we have any other questions? Okay. Next question comes from Thomas. What is the minimum time? What is the minimum time of the inrush current should be taken into account?
It's not like that the minimum time, it's about the multiplication of the working current. So if any connector has, like example, 2 amps, and if you want to use it 2 times of the working current, it has to multiply by with the 4 amps. So we have given in the graphs, so how much time you can keep it. So if you want to go for the 6th time of the working current, so again, if you say 2 amps is a working current and you want to use a 6th time, that is the 12 amps. So you need to see the graph with respect of time versus time. Then you can find out the how much time you can keep it the inrush current in the system when we connect it.
Thank you. Then next question. How much does the resistance and therefore the voltage drop across the connector increase at higher temperatures?
This we cannot give how much exactly. This you need to calculate, but we can do with respect of percentage, like I've explained in the derating curve, because that depends upon the multiple factors. So we cannot give any exact values. We can just estimate the percentage theoretically. To get exact values, we have to go for the application to application and do the test doing the calculations.
Thank you. Okay, then I think we are finished. I see no more questions in the chat. So when you have any questions, please write into the chat, and then Vamsi will answer them via email in the next days. So thank you very much, Vamsi, for your time, for your presentation, and for the answers. And yeah, thank you for your attention. I hope you enjoyed it. I want to share the link to our homepage for the Digital WE Day. So we had a lot of other sessions planned during this week. So yeah, check it out, register now, and hopefully you see us on our next session. Have a good day, and bye-bye.